Welcome to the first session of the Everything But the Engine Components webinar series, where we take a look at the components that drive efficiency, performance, and innovation across Cummins. I'm joined with Sean Leslie, Global Application Engineering Director. Could you tell us a little bit about yourself, your background, what got you to Cummins, and what you do here?
Thank you, Chase. Like you said, my name is Sean Leslie. I lead the Global Application Engineering team in our Cummins Components and Software organization. I've been with Cummins for 15 years now, but I do have coming on 25 years of experience in the diesel engine industry, primarily in the turbocharger space.
Wonderful. So for the folks who might not be that deep into this tech, why don't we start from the beginning and you just tell me a little bit about what is a turbo? What does a turbo actually do?
Yeah, turbo is actually a really kind of a cool device, right? So when you think about how an internal combustion engine works, an internal combustion engine needs fuel and it needs air. And the more fuel you can burn, the more power you make, right? So a turbocharger actually takes some of the wasted energy that comes out of the exhaust and converts it into more air going into the engine. So in a gasoline passenger car engine, for example, you just get more power, you get more performance. In a diesel engine, it's actually twofold. You can get more performance, but you can also get improved emissions, because with a diesel engine, your emissions are tied to how well you can burn the fuel in the combustion chamber. So like I said, with a turbo, not only are you getting that additional air to get more fuel to make more power out of the engine, but you're also getting a more complete combustion, thereby also improving your emissions performance.
And I could be making this up. So I feel like I've heard somewhere before that in some areas there is spaces where the air that comes out of the engine in the car, because of those emissions improvements, is actually cleaner than what goes into it. Have you heard of that? Is that true?
Yeah, I mean, it all comes down to how efficiently you're able to combust, right? So, when you think about, the emissions coming out of an internal combustion engine, it's essentially a makeup of what's going in. So when you think of what's going in is you've got air. Air is made up of oxygen, there's nitrogen in the air, right? And then you've got fuel. Fuel is carbon-based. So you've got carbon in the fuel, you've got some oxygen. So really what's coming out of your tailpipe is just a makeup of both of those, or all of those elements, right? I think it's just how those elements ultimately come together that create the emissions. So when you think about particulate matter, particulate is carbon-based, right? So when you look at smoke coming out of a diesel engine, that smoke is just carbon, right? That's unburnt fuel. When you look at, what causes smog, which you'll hear people refer to as NOx, right? So NOx is just a combination of the nitrogen and oxygen. So, in a diesel engine, you've got an excess of air going into the engine. And through the combustion process, given the temperatures, the rate of heat release, right, what happens is you're actually locking in a not very naturally forming combination of nitrogen and oxygen, and that's called, it's NOx, the X, being a sub-reference to the number of oxygen atoms that could be part of that equation, right? So, so when you think about what's coming out of the engine, they're all the naturally forming elements. So how you manage some of, the emissions coming out through the combustion process, through after treatment, yeah, arguably you could be potentially cleaner coming out than what you have coming in.
That's fascinating, honestly. So kind of going off of that, how does the turbocharger really work together with those emission systems?
So, so we've got a couple of components here in front of us, right? So, maybe I can start with really what makes up the turbocharger. So when you think about, when you look at a turbo, you essentially have a turbine stage. We call that, sometimes refer to that as the hot end of the turbo. That's where the exhaust comes in, and that exhaust energy is converted into rotational energy.
And where would that be, like on
So if you look at, this turbo, it's kind of a, facing us, but away from the audience here. But on this little makeup that doesn't have the end housing, it's essentially this end of the turbo, right? So that's essentially the turbine end. And what you have is sometimes it's called the center section, center housing, rotating assembly, right? This essentially right here is what we would call the center section of the turbo. It makes up the wheels, it makes up the bearing housing or the center housing, and that center housing holds the bearings and the shaft, right? So really that's the spinny bits, right? And then you have the cold end of the turbo, which is kind of hidden here by this electric mechanism for VGE machines. But you have essentially your compressor stage, or the cold side of the turbo, and that's where all of the pressure generation occurs, right? So as the exhaust comes into the turbo, right, you're spinning your turbine wheel around. When you spin the turbine wheel, what that's doing is then it's taking that exhaust energy, transferring it through rotational energy, and then converting it into pressure energy on the compressor stage. So when you see this compressor wheel, it's essentially designed to take air in at, say, an ambient temperature and pressure, and then force that air out at a much higher pressure, and hopefully, right, you minimize how much temperature you're adding as you're going through that compression process.
We're talking a lot about maximizing engine performance through turbocharger design. Mm-hmm. When you're designing a turbo, what are some of the key factors that you might look at that could improve that engine efficiency?
When you think about, essentially starting at an engine level, really at the end of the day, it comes down to how, your fuel efficiency, or what we call brake-specific fuel consumption, is really dependent upon how efficiently that engine converts the fuel energy into power that comes out of the crank, right? And there are a variety of factors that impact that, and the turbo can have an impact on some of those factors. So, the big one, we call it volumetric efficiency, is really just a function of how well the engine breathes. And what can happen with a turbocharger, right, is in your effort to try and recover energy out of the exhaust, you're essentially creating back pressure on the engine. So think of putting a banana in a tailpipe, right?
Classic, absolutely.
The engine doesn't want to work very well when you add a banana in the tailpipe. So when you're trying to harness some of that exhaust energy, really at the end of the day, the turbine end is creating a bit of back pressure on the engine. So what we need to do is we need to minimize the impact that back pressure has on the engine's ability to breathe, while maximizing the amount of energy that we can recover from the turbine end, right? So, from a turbine stage, what we do is we look at clearances. We look at, in the case of what we have here is one of our VG products, which is variable geometry. So, within the variable geometry turbine stage, we have a sliding nozzle. There's clearances in there that can create leakage, right? That leakage reduces efficiency. And by reducing efficiency, that increases back pressure, which, from a fuel economy perspective, isn't good. So what we do is, like I said, we look at how do you reduce clearances. In the case of the VG, we recently released products that have we call it our patented MCS, or multi-clearance shroud technology, which actually significantly reduces some of those clearances, significantly increasing the efficiency of the turbine stage. And that increase in efficiency in the turbine stage then results in a significant improvement in fuel economy. We also look at, when you look at the center section of the turbocharger, right, the bearings in the turbocharger have an efficiency associated with them. And the lower that efficiency, the less that exhaust energy which which is being converted into rotational energy, right? The less amount of energy then gets transferred to the compressor to generate boost pressure, right? So what we've done in some cases, or what we've recently released, is a roller element bearing in the center stage. And that roller element bearing helps increase the efficiency of the bearing system. And that efficiency then improves the amount of boost pressure we can then generate on the compressor stage. And then finally, on the compressor stage, when you're compressing air, just by the ideal gas law, right? When you compress air, you generate heat, mm-hmm. right? And what happens on a comp stage is, as you're compressing that air, some of that compression goes to increasing pressure, some of it goes to increasing temperature. What we want to do is in 100% efficient, comp stage, right? You're gonna follow your ideal gas law, but the reality is that you're only able to get, say, 75 to 80%, or I think we're up to, in some cases, up over 80% efficiency on the compressor stage, right? Then what you're doing is you're maximizing how much pressure you're generating, and you're minimizing the temperature. And so by maximizing the pressure, right, that means more air density going into the engine.
You mentioned, 75, 80% in that compressor stage, right? What is kind of standard, or where's that kind of been historically? I'm just curious of how that's, been improved on, how we've kind of, made that more mm-hmm. efficient.
Yeah, so and that's a tough question to answer, because a lot of times it depends on the size of the turbo, right? So when you think about, how much efficiency you can generate, we're in our high horsepower size range, where, we've got, really large turbos. I mean, our biggest turbo is probably about the size of this coffee table, right? So, in those big turbos, you can get, I can't think off the top of my head, but I want to say, 85 to 90% efficiency. So the big driver there is around the clearances. So you can imagine that, one of the key design criteria when you're looking at maximizing efficiency in a comp stage is the clearance you have between the wheel and the housing, right? So when you think of this compressor mm-hmm. cover here, and this compressor wheel here, you've got a clearance between this blade and that housing, right? Now, that clearance is going to be the same whether it's this little compressor wheel, right, or whether it's a 150 millimeter diameter compressor wheel. So, you can imagine that clearance doesn't scale. So the impact that clearance has on the efficiency on a small turbo like this is much more significant than on a bigger turbo, right? So these smaller turbos they don't have the same amount of peak efficiency as you can get from like a high horsepower turbo. So now it's definitely evolved. I mean, in the years that I've been working in turbochargers, it's amazing to see how far we've come in terms of efficiency. I mean, we're achieving efficiencies today that I never thought were possible even, say, 6 years ago. There's definitely an evolution.
What do you think is driving some of those efficiencies that were unimaginable to you?
I mean, I think there's been improvements in the analytical tools, understanding of the key factors that go into the design. There are new technologies. So, I mentioned the clearances, right? One of the things that we've done to try and improve clearances on the compressor stage is we've used an abradable technology. So what you actually do is on the inner surface of the compressor cover, you apply an abradable that's essentially ceramic based. And what you do is you design in an interference fit between the housing and the impeller or the compressor wheel. And then what you do is through the manufacturing process, you run through a bedding in process, and now you have the tightest clearance possible. And so that is another way to maximize efficiency. So, through those technologies, such as the abradables, like I said, better understanding of the different factors, and improved design tools. So there's a technology used on the compressor stage. It's called a vane diffuser, right? So, when you think of, and it may be taking a step back, right? When you look at a compressor stage, you've got your wheel, right? And so what's happening is your wheel is spinning, it's taking air in, it's going across these blades, you're increasing pressures, you're increasing velocities. And then what you have is you've got this diffuser face. So you can imagine that, on the other half of the turbo, you've got a similar flat surface. And so the air is going into that diffuser, and it's what this diffuser is essentially doing is it's converting, kinetic energy into pressure energy. And so when you go into the volute, which is this outer piece, we call it a scroll, or some people refer to it as the snail, right? That's where it really gets converted into pressure energy. Now what happens though is you go across this diffuser face, you get turbulent air, right? Because you can imagine this wheel, depending on the size of the turbo, this wheel could be spinning anywhere from, say 100,000 RPM to 200,000 RPM. So it's really fast. And so the air in this diffuser face, can become quite turbulent. And that turbulence reduces efficiency. So you can add vanes on this diffuser face, and those vanes can help to eliminate some of that turbulence or reduce that turbulence. And essentially you're increasing the efficiency of that kinetic energy to pressure energy conversion, right? So, there's another technology that's being looked at to help improve that. Now, what's interesting is when you think about vane diffusers have actually been around the turbo industry for many years. But they've been primarily focused in, like high horsepower, off-highway applications, because the diffusers those vane diffusers historically give you a very narrow compressor map. So, that narrowness in the compressor map means you've got a very narrow flow range within which you can operate on the turbo. And so it means that you can really only use it in certain applications where you don't need a wide map. So on highway trucks, because of the way the power torque curve is, historically you need a wide map. Applications like a genset where you're operating at a single engine speed, you can get away with a narrow map, right? Now, the nice thing with the vane diffuser, right, is you can get a narrow map, but you get high efficiency and you can get higher peak pressures, right? That's been the conventional wisdom for years. But what's starting to happen is people have actually started to look at how do you actually go and make the map just as wide. So how do you get the advantage of a vane compressor without all the disadvantages? And so through a lot of the analytical tools that are out now, we're starting to get a better understanding of that so that we can start looking at how do we actually use vane compressors in an on-highway truck application, right? Because now you're starting to eliminate some of those trade-offs.
So you mentioned a few terms there, the compressor map and the turbine map. What do those actually show?
That's good question. So, when you think of like, compressor is essentially a pump, right? And in a pump, you've got flow, you've got pressure, you've got efficiency and speed. So, a compressor map is really just a map of, or maybe a better way to refer to it is it's essentially a graph, right? Where you've got pressure ratio on the y-axis. So pressure ratio is just essentially, it's your output pressure divided by your inlet pressure, and your inlet pressure is usually ambient. So, if I say a a pressure ratio of 5:1, that means that I've increased from ambient 5 times. So, so that's usually your y-axis. Your x-axis is typically your mass flow. So that's just, you know, the amount of air that you're moving through the compressor stage. And then, you know, the maps have islands of efficiency, right? So usually you get peak efficiency in the center of the map. And then you've got speed lines that are across. If I'd thought about it, I probably would have pulled one together to show as part of this webinar to make things a little easier. But usually the maps are bound on, you know, the left side of the map by what we call surge. So it's at low mass flows. What can tend to happen is when the air is coming through the compressor stage at very low flows but high pressure ratios, you essentially get flow reversals within the comp stage. And those flow reversals result in what's called surge. Now, most people think of surge and they think of an engine surging, like whoa, whoa. What happens when you get a turbo going into surge, you get a pop. Or, you know, people like to refer to it as a chuff. So, you know, you'll hear an engine going down the road and they'll let off the throttle and you hear like a poof, 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 poof. That's a chuffing, and that's just a surge, you know, light surge on the comp stage. The other side of the compressor map is usually defined by its choke. And so the choke is, you know, when you think about this diffuser face, right, you've got a very narrow gap. You can only push so much air mass flow through that nozzle before you essentially hit choke flow, and that's typically defined by the Mach velocity of the air. So once you've hit that Mach point, what happens is you can't flow any more air. You can keep increasing the speed of the turbo as much as you want, but the mass flow won't increase, right? So you've essentially choked that out. So that's usually kind of how, you know, those compressor maps are defined. Turbine maps are a little bit different. You know, they typically are, you know, from a definition perspective, they're typically similar. You know, you've got, rather than pressure ratio, you've got expansion ratio, but you also have mass flow. But how the map looks is typically very different.
So not every turbo fits every engine, right? Mm-hmm. So what goes into picking the right one for a specific application?
Yeah, that's a very good question. You know, because we look at the turbos on the table here, right? I'm not, you know, you don't want to put this thing on a, you know, little 1.5 liter engine, mm-hmm. or this thing on a 95 liter.
Probably not.
So, you know, how you match a turbo to an engine is you usually start with the compressor stage. So, you know, the compressor stage is defined by how much air the engine needs. So, you know, usually, so in my role, right, in application engineering, my team's responsible for essentially selecting the right combination of parts to meet the performance needs of a customer's engine. So first thing we do is we look at, okay, what's the engine displacement? Because that usually defines the volume of air. So a 15 liter engine, right, that defines for you the amount of volume of air that needs to go through the engine. So you need displacement, you need power. Usually, you know, we need to know the air-fuel ratio, right? So taking some of those key parameters, we pick out a compressor map. So usually in matching, the compressor map selection is the easiest part. Now, what you have to do when you look at the turbine stage is you look at how much exhaust flow is going through the turbine. You've got to look at some of the pressure conditions and then essentially use that to figure out, okay, you know, and maybe backing up. You look at the compressor stage, that defines how you need to know how much energy is needed or power is needed to drive that compressor stage at the points that you need to drive it at, right? So then what you have to do is you have to go and find a turbine stage, given some of the exhaust mass flow parameters and pressures around it, that will actually achieve those target powers, right? So it's the the black art of matching is usually in trying to figure out or select the right turbine stage to go with the compressor stage.
So how do things like altitude or the torque curve requirements come into play when you're choosing that correct turbo?
So, altitude's an interesting one, because what altitude does is altitude then drops your ambient pressure, right? So the amount of pressure at sea level is higher than the amount of pressure you have in Denver, right? So what a turbo does is a turbo, of course, increases the pressure going into the engine. Now, if you want to achieve the same amount of power in Denver as you do, in Columbus, for example, right? What that means is you've got to generate more pressure using the turbocharger. And what can happen is that by increasing that pressure demand on the turbo, you're essentially increasing the pressure ratio, increasing the turbo speed. And so when you're looking at a turbo match, right, and looking at a compressor match, you have to take that into account, because if you exceed the speed limit of the turbo, right, then you can have failures at altitude. So, when you think about this impeller or this compressor wheel here, as I mentioned earlier, this thing's spinning, anywhere from 100,000 to 200,000 RPM, depending on the size of the turbo. So the stresses on this are really high, right? So your speed limit is usually a function of the stresses in that wheel, right? So when you're matching for altitude, you have to make sure that you're not exceeding the stress limit or the design speed limit of the compressor. The other piece that we typically account for too is we have to account for fatigue. So you can imagine these really high stresses as this wheel's spinning, right? If you're running at constant, you're at a constant stress. Now think of the last time you were on a transit bus or a city bus. That city bus is accelerating really fast, goes up to 150,000 RPM on the turbo speed, and then they go to the next bus stop a block later, on the brake, turbo back down to idle at 10,000 RPM, right? And then they accelerate all the way up. So what happens is, think of it like a paper clip. This compressor wheel's now acting like a paper clip, and eventually it'll fatigue and break. So when we think of, altitude or even sea level, right, we have to account for the low cycle fatigue, and usually that lowers the speed limit a little bit. So, if you have a max design speed of, say, 100,000 RPM, and you're going in a highly cyclic application, we might say, hey, your speed limit's 80% of that, right? So, so that's usually how we account for the altitude element. You mentioned torque curve. So the torque curve, as I mentioned earlier, right, the turbo map or the compressor map is defined by its one element of its width, right? So how wide that map is. So if you have an engine that has a really high engine speed operating range, right, you'll need a wide map. But the other piece of that is if you have really aggressive low speed torque requirements, right, that means that you're operating at a low portion of that compressor map. But that can also have an effect on just how wide the map is. The other key piece there, though, is when you think about that torque curve and where you want your peak torque, then comes down to how you match your turbine stage. So if you need, a lot of torque at a low engine speed, you need a lot of power or a lot of energy in the turbine stage early on.
What are some situations or applications where that might come into play?
So on highway truck, right, there's a lot of this down speeding now. So, you want peak torque at lower engine speeds. So that's maybe a situation. Maybe I'll use a slightly different example, right? So when you think about, I'll flip it over to a pass car. In the early days of turbocharging and gasoline engines, you always heard reference of turbo lag, right? And so when you think about the amount of, you've got to spool this up before you can actually generate boost, right? So the time between, generating that energy within the engine and that exhaust energy then entering the turbine stage and then creating that rotation and boost, that's usually referred to as turbo lag. Now you can address that through going to a smaller turbine stage. You can address that through going with a VG, a variable geometry turbine stage. So those are tricks that you can do to create better low-end torque response, transient response. But then usually there's trade-offs. If I go to a smaller turbine stage, I mentioned earlier, right around, the banana in the tailpipe. Well, by going smaller, you're putting a banana in the tailpipe, so you're less efficient. So, you've got to account for that consideration as well.
Makes sense. So when you're dialing in this turbo's design overall, what kind of features can be adjusted, like the blade shape, diffuser geometry, anything like that?
Usually, you see these blades, the way they're shaped, number of blades. Those are all key factors in designing, the compressor wheel or even the turbine wheel, right? Those really define how well you're able to, those really dictate the performance, right? So it's, blade geometry, everything you mentioned there, blade geometry, diffuser design. The other thing is the what I mentioned earlier, the volute, right? So, on a turbine stage, this volute on a non-VG turbine stage, this volute is really critical in determining the amount of flow through the wheel. Wheel diameter has an impact on the amount of flow. We also talk about trim. So, when you think of in the case of the turbine wheel, right, this outer diameter is known as the inducer, and this smaller portion here exiting the turbine wheel is called the exducer, and that ratio is typically referred to as the squareness, or the trim is essentially the ratio of those areas.
So do you make different design choices based on the application of where the turbo might be used? So whether it's on highway, off highway?
We can. It's not, it really depends on the customer, right? So when I think of like Cummins, in a lot of cases, we might just repurpose the on-highway product and use it in the off-highway market. We just have to make sure that, the turbo itself fulfills our requirements from a durability perspective. But there are times where, if the customer really wants to maximize the performance, you can go and do more unique matches to fulfill those needs. So I mentioned earlier the vane compressor is a great example. We've recently released our HE850 turbocharger, which has a vane compressor, and that has significant benefits in the power gen market, right? Because a genset will typically only operate at 1500 RPM or 1800 RPM. And so they have a very narrow operating speed range, and so we can take advantage of that vane compressor technology to maximize performance, within their narrow operating range. I think the other, I mentioned earlier, low cycle fatigue. Sometimes, we might need to, count for that, in our speed limits. Sometimes we may even need to use titanium and the compressor wheel. So,
great. So you were telling me a little bit about this model here, and you mentioned this part up here. Could you go a little bit more in detail? Kind of tell me a little bit more about that.
Yeah. So, as we think about the future, right? there's a future in electrification, right? We talk about hybrid powertrains, mild hybrid powertrains, and how do you leverage electrification to maximize the performance of the product. So what we've been looking at is how do we electrify turbochargers. You've seen it in racing and past car where actually the turbocharger is being used not only to generate boost pressure for the engine, but also to harvest harvest energy in the form of electricity, right? So what we've done is we've actually been looking at, I'd say it's a fairly simple solution because it allows us to use our full product range theoretically, right? But it's essentially adding a motor generator unit on the compressor. So this motor generator unit here is essentially a large air gap motor. And so at the tip of the compressor wheel, so on this little mock-up here, if you think of this nut, this impeller lock nut, this gets replaced by a long magnet. And that magnet sits inside the stator. And so as that magnet spins, it generates electricity. Or vice versa, you can turn it into a motor and essentially then have boost on demand. So this is one of those things that we're looking at to kind of protect for the future. I mean, you think about it, there's some really cool benefits. From a BSFC perspective, you're essentially, harvesting that lost exhaust energy, and not only can you use it to generate boost pressure for air into the engine, but you can also then use it to generate electricity to power other electronic devices on the engine. And when you do that, that means that you can take other electrical generating sources off the engine, which typically act as parasitic losses, and that then results in a net benefit in BSFC.
Wonderful.
But the flip side of it, like I said, is you can use it as an e-booster as well. So, that helps improve transient response, gives you air where you might need it, but the turbo isn't ready to generate it yet, right? So
for someone who's watching this, who might be speccing a system or just learning, what's your big takeaway on turbochargers and performance?
So really, when you think about the performance of the turbo and how it pertains to the performance of the engine, it really just comes down to the culmination of the components and the technologies that are selected that make up the turbocharger.
Excellent. Thank you so much. I appreciate the conversation today. We're going to move into a Q&A portion now. So we'll go look at our chat, talk to our audience a little bit, and Sean can share some more of his knowledge.